Okay, welcome back to our lecture on the history and philosophy of science. This is the third and final part. We had finished up the last section by talking about Isaac Newton, and we're going to move on and discuss the guidelines for modern science that he proposed that still apply today. So these are Newton's guidelines for science, and let's walk through each of these in a little bit of detail. First and foremost, Newton said that science should always provide laws that are universal, so laws that can be applied in all situations. According to Newton, developing a law that only has limited applications makes it poor science. So any discoveries we make about science should hopefully provide laws that can be applied in all settings. The law should be given a precise mathematical formulation and allow detailed application to complex systems. So you need to be specific. You need to utilize mathematics to be specific about the laws and then allow for them to be applied in very detailed ways to these complex systems in the world we're studying, like physics. Hypothetical entities and forces are permitted, but only if their effects can be directly observed and measured. This is a very interesting concept. I think this both addresses the issue of theology that was so dominant at the time, but also the idea of forces we can't explain, like gravity. So in the case of Newton, he recognized that gravity was an unknown force that allowed objects to manipulate one another from a distance without contact. But he said the reason why I allow for gravity in my theories of motion, is because their effects can be directly observed and measured. The ultimate judge of a theory should be direct experience rather than philosophical, political, or religious authority. This is an important and very relevant tenet for us to apply to modern science as well. This is going back to how Newton essentially is a follower of Aristotle. He does believe that direct experience and observation is the way in which we understand the world. But he's also touching on the fact that Galileo was persecuted for a theory that is, now we know to be accurate, and at least at the time was more accurate in terms of the measurements that it showed when you looked at the world around you. So a theory should not be judged by by philosophical, political, or religious authority. So he's talking about not having subjective influence get in the way of arriving at objective findings based upon evidence. And then he finally proposed that an adoption of the corpuscularian assumption that the features of large-scale objects and processes should be accounted for in terms of the motions and interactions of their smaller parts. Now, corpuscularian is a $10 word, but essentially what he's saying is that large-scale objects and processes can usually be accounted for by looking at the smaller parts that make them up and how they interact. And this has a lot of implications for things like atomic and subatomic theory. But basically what he's saying is that large-scale things can often be broken down into their component parts, and this is often a good way to explain them and understand them. So as we go through the class, I want you to think about these guidelines for science and how they apply to our study of psychology as well. So, if you go back to the beginning of this lecture, we talked about epistemology, right? And epistemology are ways of knowing things, like how do we understand our process of knowing? So epistemology is always interested in things like how do our senses interact with our reason to understand the world? How do we arrive at something as evidence? And what's emerging in this process in the West, especially between Plato and Aristotle to some extent, but really what, in terms of the actual theories that come out of it, is a conflict between two different competing epistemologies, and we call them empiricism and rationalism. Empiricism can be thought of as really being the Aristotelian thread, and rationalism as the Platonic one, the one that comes from Plato. So it's not as simple as that, but ultimately these were the two schools of thought that were emerging in the development of Western science. And let's walk through each of them in a little bit of detail. Empiricism essentially says that experience has primacy in human knowledge and justified belief. That means observation, the things we actually see from the world, things we can measure based upon our sense experience. And it was really stimulated by the rise of experimental science, the idea of doing systematic observations and measurements of things in the real world. And so empiricism really gets its feet underneath it in the 17th and 18th centuries. And we associate this with people like John Locke, George Berkeley, David Hume. These are often regarded, many of them, as what they call early modern philosophers. And what they really arrive at, which flies in the face of what Plato was saying, many centuries earlier, is there is no such thing as innate knowledge. All knowledge is derived through experience and observation. You don't just know things intuitively. Now, competing with that is the concept of rationalism, which says that reason has precedence over other ways of acquiring knowledge. This is very much what Descartes was arguing in this idea of the cogito. He was saying, my observations can be flawed. I could be manipulated. I could be a jar, a brain in a jar being manipulated by a mad scientist somewhere. But that reason is really the way in which we understand and is the unique path to knowledge. Proponents, as I said, include Descartes, Leibniz, Spinoza, other early modern philosophers, and they do believe that there are certain forms of innate knowledge. Now, when you go back and you read Descartes' Meditations on First Philosophy, it's fascinating and it has applications for tons of things about science, but you can't forget where he's coming from. He was a very religious person, and he wanted to be able to make a strong argument that God existed, that God was real. At the time, that was a very common endeavor for these early scientists and philosophers, was proofs and theorems, trying to basically argue utilizing this new idea of reason in science for God's existence. And so, when you get to the end of Meditations on First Philosophy, what Descartes is really doing is he's trying to provide a brief treatise that says that God is real and I can prove it. Now, for people like Noam Chomsky, modern linguist and obviously huge figure in science, for him language is innate. Chomsky theorized something called the language acquisition device in the brain. It's the reason why it's harder for you to learn a language as you get older, but very easy for infants to become bilingual or trilingual or quadrilingual even. What he says is there is this natural tendency towards understanding language in the brain that is innate, that comes with us the minute we're born, and that essentially it gets differentiated by whatever we hear, whatever we're exposed to. But according to him, language is innate, that it is the way we structure our understanding of reality. Leibniz said the same thing for logic. He felt like logic was this thing that existed innately, was not just a creation of man, but that we tapped into and understood. So really, you've got this competition between empiricism and rationalism that emerges in the scientific revolution, and will continue to ebb and flow in various ways. Neither of them is entirely a 100% dominant. But when you look at modern scientific research, including psychology, we rely much more heavily on empiricism than rationalism. So at the end of this, can we define science? What do we mean to say that we're doing science? See, really, science came into its own in the 17th century, but it didn't sever all of its connections to its origins in philosophy and religion. It was really something that was struggling with where it came from and where it was going. So it begs the question, these early figures that we're talking about in this lecture, were they practicing science? Were they doing science? Was Descartes doing science? Was Newton doing science when he practiced alchemy, for example? He, as brilliant as Newton was, he believed in a lot of very strange things and was a very eccentric character. These early Milesian cosmologists, these first scientists like Anaximander and Democritus, these first philosophers who were coming up with the ideas of what is the world made of, was that science or was that really philosophy? So we have to think at first, what would a good definition of science look like? What sort of criteria does it need to have to be a good definition? So when we're trying to define science, we want to be careful not to be too broad. If we're too broad in our definition, then that includes activities that are clearly not science. So for example, an early definition of science you might come across is science strives to represent the natural world. Okay, well, what about landscape artists? If you're sitting on the edge of a stream and painting a beautiful field, most people would agree that that's not science, but you are attempting to represent the natural world. So that's too broad a definition. It captures things that we all agree don't constitute science, at least by our modern understanding. Too narrow a definition might exclude areas of study that are generally regarded to be science. There's an emphasis on the necessary use of mathematics. Well, this might exclude a lot of aspects at least, of archaeology and geology. These are all things most of us agree, are sciences. So if we're too narrow in our definition, then we lock out things that we all kind of tend to intuitively think of as science. Ultimately, science always aims to explain. Okay? Explanation of the universe around us, it begins with the earliest scientists, including the earliest philosophers, right? They are all trying to make sense of the world that they interact with, that they observe around them. And that is, right up until today, one of the key things that is a component of science, is an attempt to explain the natural world, the world around us. And it likely relies on theories in doing so. So let's think of a working definition of science that might include this, okay? Um, the use of theories, sometimes mathematical, to explain natural processes and systems. So this is a working definition of science we can begin with. Now, natural is defined liberally enough in this definition to include all uniquely human behavior, allowing for sciences like psychology and economics to be included. So we're not just talking about, natural things that occur in the world like the movement of the planets or physics, but, things that derive naturally and include human behavior like our minds, which then leads to thoughts, feelings, emotions, things that are studied in psychology, and of course behavior. Economics, of course, is an example of something that's not necessarily objectively observable in the world, but it is studied scientifically in a lot of ways. This definition then might be a little too broad because it does not exclusively attempt to explain natural phenomena. For example, a religious explanation of a recovery from an illness is an attempt to use a theory to explain a natural process, but it doesn't qualify as science. So as we're working with this, as we're struggling a little bit, we find that most definitions of science are going to fall down in one way or another. It's a very hard thing to properly define, but there is one option I want to consider and I want you to think about this as the class continues. So let's talk a little bit about Karl Popper. Karl Popper was a 20th century philosopher who lived in Vienna in the 1920s, and he was very inspired by Einstein, especially his new and his general theories of relativity. He was less impressed by other emerging theories like Freudian psychology and Marxist historical theory. So Popper was concerned that things like, the psychology that Freud was practicing, as we, which is of course very dissimilar to modern psychology, and Marxist historical theory on economics, like things like capital and supply and demand and things such as that. He basically said, well, I'm not sure these should qualify as science. So what differentiates them from science? And he came forward with the idea that a theory is scientific to the extent that it is falsifiable by empirical tests. Now, this is, you talk about foundational grounded important aspects of how we define science. This is really, really crucial. A theory is scientific to the extent that it is falsifiable. The fact it can be proven wrong. It must be possible to refute the theory by making empirical predictions or tests. So corroboration for a theory is provided by passing these tests, by going through a series of experimentation and scientific investigation and still holding up under scrutiny, at least until the next attempt comes along that attempts to refute it. Popper also recognized that theory could easily degenerate into dogma. Dogma being absolutist statements about the reality of the world or about the way that the world works. There was this theory called the phlogiston theory about combustion in the 19th century, and it basically it was kind of an offshoot of the concept of ether, which I'm sure you've never heard of, the idea of the ether that exists in the universe. These were early theories of physics that have since been disproven. There was a long-standing theory that anytime there was combustion or fire, that there was the creation of a substance called phlogiston, but phlogiston couldn't be measured, it couldn't be defined clearly, it couldn't be witnessed or observed in any way, but nevertheless it persisted into the 19th century when we had pretty decent understandings of the physics behind fire and combustion. So he was pointing to that as an example, but even in a larger sense, it's really important that we recognize that theory, if it is taken to an extreme, degenerates into dogma, which cannot be refuted. Dogma is always proposed to be absolute. Critics of Popper challenge this falsification theory, as it's called. It's also called the demarcation criterion. Because of its emphasis on falsification, the notion that theories are scrapped if in the face of any false content. And I think that's really a misreading of what Popper is talking about. For example, Galileo proposed circular orbits, but yet a lot of the things that he had to say about a heliocentric model of the solar system were accurate. But you might look at it and say, nope, he said there were circular orbits, therefore it's all garbage and we throw it out. Well, Johannes Kepler comes along and he comes up with the idea of elliptical orbits. We still hold on to aspects of Galileo's theory as being correct. Now, that's not really how theories work, and as I said, it's maybe an overly simplified way. So critics of Popper basically say, well, if you take falsification as your absolute criteria, well, that means a lot of theories that are actually pretty good but need some tweaking would get dismissed. So sticking with a theory, even when it requires these little ad hoc repairs, is not always a bad thing. So for example, it can be a bad thing. We think about the geocentric model we discussed in the earlier part of this lecture. And I mentioned that the people that supported the idea that the Earth was the center of the system had to constantly make repairs and changes, right? And they held on to their theory in that sense. And in this case, we now know they were inaccurate in doing so. But there were aberrations, for example, in the observable path of Uranus, right? And so when astronomers would study this, they would constantly say, well, maybe we need to, change our theory, but these aberrations don't make sense, they don't add up. But by holding on to that theory and exploring it fuller, to a greater extent, what they eventually discovered was Neptune, right? There were gravitational pulls associated with Neptune, which was not observable, but they clearly knew that it was there later because of these aberrations in the path of Uranus. So again, we don't always throw the baby out with the bathwater, right? We don't want to discard a theory altogether simply because there are some problems with it, but we do want to propose theories that are able to be refuted and falsified by empirical testing. That is a crucial aspect of what we're going to talk about throughout this class. So when I discuss philosophy of science, what do I mean by that? So philosophy of science is a subfield of philosophy, and it's concerned with the foundations, the methods, the implications of science. The central questions of this type of study concern what qualifies as science, the reliability of scientific theories, and what's the ultimate purpose of science. So this discipline overlaps with things like metaphysics, we talked about, specifically ontology, epistemology, how do we come to know things. For example, when it explores the relationship between science and truth with a capital T, right? The concept of truth as an absolute. We certainly find philosophy of science discussing this issue and how does science work and how do we come to know things. But really what it's doing, and when we practice philosophy of science, we're attempting to understand the fundamental questions that surround science. And these are some of the things you might think of. Is scientific knowledge different from other sorts of knowledge? Is science getting closer to some form of absolute truth? Can science reveal the truth about unobservable things? Now that's an interesting concept, right? You think about gravity as a good example. We can't observe it directly, but we can certainly, we can posit that it exists based upon observations of objects. What is the ultimate purpose of science? Why do we practice science? And how is it ethically applied? This is an extremely important one too, and it has serious implications for things like medicine. What counts as a good scientific finding? How do we know if it's a good scientific finding or a mediocre one? How is science influenced by politics, religion, economics, gender issues? These are all things we need to consider as well. Science does not exist in a vacuum. It exists in the human world that we all share, and it can be influenced by a lot of things that have nothing to do with science. And so philosophy of science sometimes seeks to parse those things out. There are also questions that are specific to particular fields. There's not just philosophy of science. Within that, there are subtypes: the philosophy of astronomy, the philosophy of genetics. There's all these things. Things like artificial intelligence have a whole philosophy of science behind them as well. I want to finish up this lecture by a discussion about something I'm going to refer to as the danger of certainty. And at the very end of the lecture, I'm going to include a link to a YouTube video that I would like you to watch. It's something that I saw in a class years ago. It's an old series from the BBC. I believe it was made in the 1960s, maybe the 1970s, I'm not sure. But it was called The Ascent of Man, and Jay Bernowski was a famous scientist who hosted the show. And I'm going to have you watch a small clip of it in a moment. But this whole episode of The Ascent of Man is really about certainty and the dangers of certainty. He talks a lot about our tolerance for uncertainty within science. So many people have misunderstood and misapplied science as a crusade for absolute truth, truth with a capital T, right? This runs contrary to the basic tenets of science, which is that things are falsifiable, right? We never claim that any scientific finding is absolutely unassailably true, because then we have taken a step towards dogma, right? We are now no longer practicing science. We have to appreciate that the scientific method, or empiricism as we're going to refer to it later, is simply one approach, paradigm, or worldview for making sense of the world, including human behavior and psychology research. Like all paradigms, a belief in its absolute infallibility as an approach leads to dogmatic certainty, and then it is resistant to alternative evidence. If I believe that my theory is 100% unassailably true, when I'm confronted with alternative evidence, I'm going to disregard it, even if that evidence is good, even if that evidence is derived through good empirical research. And unfortunately, history has shown that individuals and groups of human beings claiming absolute truth are capable of monstrous acts justified via that same certainty. You don't have to look much further than the Holocaust or the actions of Nazi Germany to come to this conclusion. There are plenty of examples of people, committing atrocities and horrific acts on the backs of a claim of absolute truth or certainty about something regarding the world around us or human behavior. So scientific behavior comes with a responsibility to never degrade our scientific endeavors into dogma, to understand that as great or as well supported as a theory might be, it is always potentially falsifiable. We must always maintain a degree of humility in the face of science, that we never claim to have absolute truth. Now, theories that are continuously and frequently supported over and over and over and over, we start to have some faith and some trust in those theories, and we will often defend them more vigorously than we might a less supported theory. But we have to be careful of not stepping over that line into absolute certainty. In the Bernowski video I'm going to have you watch, in the whole episode, he talks about how science has a tolerance for uncertainty. And we're going to talk about this in very practical terms as the class goes on, in things like what we call p-values. You know, how likely is it the thing we found was just due to chance, or was it really due to what we manipulated in our experiment? Bernowski makes an important point far beyond the scope of science into real-world implications in the video that I'm going to have you watch. So please follow the link on the next slide and watch this section of an episode of The Ascent of Man. I want you to think about it, and then I want you to come to our next Zoom meeting where we ultimately are going to discuss what you think he is trying to say, what he's trying to imply, and what the implications are going forward as we begin this journey of understanding scientific research, specifically in the field of psychology. So here is the link. Please follow it and watch it before the Zoom meeting, the next Zoom meeting that we all attend, and we will talk about it more at that time. See you all then. Hope you're doing well. Thank you.